Okay. So Tyler's I'm gonna stop class about 10 minutes early today because you can fill out TA evaluations then. I've heard positive comments about Ian from a number of students, so I just encourage you, if you do think that he was helpful, that you make that known on the evaluations, because we do try to recognize the students, the grad students who sort of put in the most effort to helping the undergrads in the classes they're supposed to be TAing. So it sort of goes around, comes around. It helps encourage them to do a better job. So fill it out, honestly and correctly. But I just, we just encourage you to do it. So, okay. So the last thing that I want to introduce you to is the idea of partial differential equations.
Is this the last class?
No. So Thursday we'll work on some of this stuff.
Yeah.
Next Tuesday, I thought I'd do a review session next Tuesday.
So this is
This.
Dr. Lapp?
I'm done. Yeah. Okay. So what I want to do is to introduce you to PDEs through the equation for heat conduction. And this is something that I think that you're already encountering in your transport class, so it shouldn't be entirely unfamiliar. So if you remember, the start of this for both heat transport and mass transport, it's all the same math basically. In the case of heat conduction, there's Fourier's law, which relates the heat flux to the gradient of the temperature. So Q is a vector. Which is the heat flux. And it basically describes the rate of energy transfer across a unit area of surface, right? So it would have units of energy, and then it's not just energy, it's the rate of energy transfer. So it's joules per second, but it's not the total. The heat flux doesn't mean the total energy being transferred. It means the energy crossing a unit area of surface. So it's also got to have meters to the -2 in it. So that's units of heat flux. And this grad object, I'm not sure, it depends how whoever's teaching transport is doing that, whether they're introducing you to vector calculus. But all grad operator is a vector, but instead of being a vector that actually has numerical values, it's a vector operator. So it's perhaps simplest to write down what grad T is. So when it operates on a field, it then gives you a set of values which can be put into a vector. So it's a vector of partial derivatives. And just out of habit, I use this kind of notation to mean a partial derivative. So by dx, I just mean the partial with respect to x. To me, this is a lot neater and a lot quicker to write than writing the whole partial derivative. And it also keeps things on one line. It doesn't split things over two lines. So that's what I want to use. But the basic idea is then that something like this is a vector whose components are the partial derivatives, okay? Q isn't just a single thing. Q and T are what are called mathematically fields, and that means there's something that's defined at a bunch of points. Okay, so we talk about the temperature being defined over the whole domain, and the heat flux being defined over the whole domain, where the domain could include all the volume of the system, whatever that is, and also time as well. So for example, t in the most general case would be a function of x, y, z, and time. So it would be a function of four things, four independent variables. So note here that in contrast to ordinary differential equations, when there's only one independent variable every time, maybe many dependent variables, there's only one independent variable. Now we're dealing with problems where there can be four independent variables. So t is a function of four things now, not just one thing. And of course there can be more than one field, and these things can be either scalars or vectors, so it's becoming a little bit more elaborate. So in order to make an equation out of this, so Fourier's law is what we usually refer to as a constitutive law. It relates this flux to the primary quantity, which in this case is temperature. Now the other thing we need in order to get an equation out of all this is an energy balance. So if we first just look at an infinite slab, that basically is what you'd normally refer to as a one-dimensional energy balance. Yeah.
If it's dependent, what are the two, or no, if it's it's a PDE, what are the two dependent variables?
So a PDE may only have one dependent variable. So we're going to look at we're only going to consider the simplest case with a partial differential equation with a single dependent variable, which in the case we're going to look at is going to be temperature.
Okay.
So we're going to get an equation for temperature, which I'm sure you've seen before, and then we're going to focus on how we solve that in a couple of cases, okay? But the distinction is that the temperature will now depend on more than one thing. It won't be just temperature as a function of time. So some problems you might have come across is, I got a glass of water which is hot, write down a differential equation for temperature as a function of time, say using Newton's law of cooling. And then you just imagine how much energy was being lost from the vessel, which is usually proportional to temperature, and you'd write down an ODE that said dt was equal to minus something times t, or something like this. This is an ODE where the temperature is only a function of time, because you're not looking at temperature variation. Okay? We're going to look at problems where we're also going to consider not just a single measure, but something which is measured all over at different places in the system.
Yeah,
Okay?
we've been doing that for transport. We only do it with one thing. Temperature's a function.
So typically most of the transport class is going to focus on just t being a function of x. Yeah. So
That's so weird.
So at the end of the day, you actually have what you're having in the transport class is usually what we discussed last week, which are boundary value problems.
Yeah.
You have problems where there's only one independent variable, but your auxiliary conditions are at each end. You've got a temperature at this end, temperature at that end, something like that. Yeah. Now we're going to look at something that's a little bit more complicated, but the ideas are basically exactly the same. It's just going to be in two space variables. The reason you don't look at those problems in transport class is it's quite hard to solve those problems. What we're going to look at is how we can just use the computer to get those kind of solutions. Okay. So if we're going to do the energy balance on an infinite slab, we'd have a sort of picture like this. And these are just little areas within the slab. You've got to imagine the slab itself going on in both directions for an indefinite distance, and we just have a single coordinate here which we'll call x. So there's a heat flux here which is the x component of Q at the place x, and there's a heat flux here which is again the x component of Q, but at a slightly different position, x plus dx. Yeah? And what we're going to want to do is to calculate the rate of change of the internal energy within this slab. So imagine you've got these two things, which are two very large boundary planes, and we're talking about the stuff in between. So then I'd have an equation that said the rate of change of the energy in the slab would be the heat flux coming in. So at this point, there's heat. If QX, if we assume QX is positive, it doesn't matter about the sign. But if QX was positive, then if I'm sitting on this side, then if QX was positive, heat will be coming into the system, so the energy will be going up. And the amount of energy, the rate at which the energy will go up is QX times the area of the slab. Yeah? Because remember that the heat flux measures the energy current per unit area, so we have to multiply by the area. And that's the energy crossing this plane, or the rate at which energy is crossing the plane. Yeah? Now, it's also true that the energy is leaking out over here. So actually, I need to be a little bit more careful. So energy is leaking out from the other side. Now, in this case, if QX is positive, then energy will be coming out, so that's going to have a negative sign. And I know you've seen this before. Okay. So that gives you an energy balance on the stuff between the slab, and we're ignoring anything that's leaking out above and below. Okay. Now, if we simply rewrite Q at x plus dx, we do a Taylor expansion, then we'll get Q of x, which will cancel with this Q of x. So the only thing that matters to the energy balance is not the Q itself, but the rate at which Q is changing over the distance, over the thickness of the slab. You see? So this will give us minus, because of the sign, times the thickness of the slab, dx, or not dA, times the area of the slab, A. Okay? So that gives us the rate of energy change in the slab in terms of the derivative of the heat flux. Now the energy in the slab would just be this guy times the volume of the slab, which is dx times A. Yeah? So this is the mass density. Little e is energy per unit mass. So that's what's usually a material property of a given liquid. It at a particular density and temperature, it will have a certain energy per unit mass, which we call little e. So if that's the energy per unit mass, if I multiply by the mass density, those two things together are the energy per unit volume. Multiply it by the volume, that's the energy. Okay, so the energy in the slab is just the energy per unit mass times mass density times the volume. So then we can stick those things together. And we'll get a partial differential equation for little e. Okay? Because you see that basically the volume term has cancelled on each side of the equation. So there's a volume term here, there's a volume term in the energy. So basically that tells you how the energy in the energy density, or the energy per unit mass in the fluid, is changing. Okay? Now, all I did there was a one-dimensional energy balance. Now, we're going to want to do something a little bit more complicated than that. What we really want to do is not just consider this thing as a slab, but if you like, make it into a volume element. Okay, so not just a slice now, but now what we want to do is we imagine we've got a little volume element in the whole big system, right? So we've got some large fluid volume, and we've just focused in on a little element, and we want to write the energy balance for that element. Okay? Now the energy balance for the 3D volume is exactly what we just did, except that if I have a 3D volume, energy just doesn't come in and out on one pair of surfaces, but it does it on the other two surfaces, as pairs of surfaces as well. So if I want to do this in 3D, then I land up with this guy. Does that make sense to everybody? So that's just essentially the fairly obvious generalization of what I just did in one dimension, doing it in the y and in the z direction as well. So this then is a expression for the energy balance in general. So just in terms of heat conduction, we haven't made any specialization to one dimension or anything like that. So if we wanted to write this in a slightly more compact way, we could say that this is equal to minus the divergence of Q. Okay? So this is an operator in vector calculus. This is called a divergence. Sometimes you see it written as just div. Okay? Now what we've done here, let me make that clear. Okay? What we've done here is we've taken essentially the dot product of two vectors. So there's nothing unusual here. We've just taken the dot product of two vectors. It turns out that one of the vectors is not a quantity but an operator. All right? So if this was little a and little b, then a dot b would mean ax bx plus ay by plus az bz. Right? We've done this over and over. What div dot q just means is dx qx plus dy qy plus dz qz. So it's exactly the same concept as a dot product of two vectors, but now one of the vectors is an operator, that's all. Okay? So now we can write our energy balance in a fairly compact way. The other thing we want to take note of is that a small differential change in the internal energy is related to a change in the temperature just through the thermodynamic relation dE is Cp dt. Yeah? So if we keep the pressure fixed, which we're imagining in this system, then a small change in internal energy is related to a small change in temperature through the heat capacity. Okay. So then you see what I can do, what I'm going to be able to do here is to stick that into that relation.
Why is the constant pressure heat capacity not coming from?
Just because that's the normal way in which you would set things up. So if you're doing, say, heat conduction in a bar, for a solid it wouldn't make any difference whether it's constant volume or constant pressure. It is a little bit different if you had say a liquid confined, but usually if you're doing heat conduction in a liquid it will be open to the atmosphere, so it will be constant pressure. I mean, we're making something of a simplification here because we're, for example, ignoring buoyancy. So when the temperature changes, you change the density, and that can generate buoyancy currents. We're only thinking purely in terms of heat conduction. So then on the left-hand side, I just have rho Cp times the partial derivative of the temperature, yeah? Because I've replaced the partial derivative of little e with the partial derivative of temperature. Yeah? And that's equal to minus the divergence of Q. But from Fourier's law, Q itself is just minus lambda times the gradient of T. Now understand there's a difference between gradient and divergence. Okay? So they both look like almost the same thing, but they're different. Because what's happened is